We've seen earlier that realistic potential for vibration, say in a diatomic molecule, might look a bit different than a harmonic oscillator. And this picture that's shown here is actually a grander version of the one that was shown earlier. What I want to do is talk about a particular model that's actually a little bit more realistic and compare that model to the results that we've gotten for the harmonic oscillator. This model is something called a Morse potential or a Morse oscillator, and it has the functional form as follows. Take the potential function is equal to a constant times 1 minus e to the minus beta r minus r0, and then all the stuff in brackets is squared. All right, now in this particular expression, we have d, which actually serves the function of a dissociation energy. It basically scales this entire potential. So if the bottom is down here at the bottom of the scale, that would be 0 in energy, and this up here where the molecule dissociates or where the bond dissociates, we would have d. So that difference would be d. The parameter beta is basically a range parameter, and it's going to affect how wide this potential function is. So it's basically the width of the fall off of the potential function. And finally, R0 is just what we previously called R sub E. It's basically the bond length or the equilibrium separation between the two masses involved in this potential. All right, so from this we can see that as r goes to infinity, how does this potential vary? Well, as r goes to infinity, we'll have e to the minus infinity, which is 0, so this would just be v of r going to the dissociation energy, okay, which is exactly what's happening here. As r goes to infinity, the potential function, the blue curve here, is going to the value of d. Okay, what about as r goes to, or as r equals r0? Well, r equals r0, the curve says this should be 0. Well, up here, I have got r equals r0, so I'd have e to the 0, which is 1, and I have 1 minus 1, so that would be 0. So v of r does go to 0 in this limit. Finally, as r goes to 0, or r equals 0, what will I have? Well, for r equals 0, I'll end up with a function v of r that will equal to d times 1 minus e to the beta r0 squared. Okay, well, depending on the value of beta and r0, this is not 0, it's not infinity, it's not anything. It's probably something quite large, because this will be a positive and large number, and even though it has a minus sign, when we square it, we'll get the large number squared, but it won't be infinity. And so this is a way in which the Morse potential is perhaps not physical. We would expect that to go to quite a higher value, or higher level. All right, so when we write down the Hamiltonian for this particular system, okay, the kinetic energy term is going to be much like it was for the harmonic oscillator. We'll just have d squared dx squared times minus h bar squared over 2 mu. And this will be our potential energy part, so we'll have d times 1 minus e to the minus beta rx. I'm going to just go ahead and call this displacement variable x squared. So this is the operator that's going to be operating on wave functions in the Schrödinger equation, and the one that we would need to solve. So I've basically used x is equal to r minus r0 in this. Now, I'm not going to go through the results of that, or at least not through the process of solving it, but it turns out that the Morse potential is another one of those rare problems in one dimension that actually can be solved exactly, and has been solved exactly. All right, the net result of this, and I'll put this in a little bit different color, is that the energy levels of the Morse oscillator can be written as follows. They're equal to h bar beta times the square root of 2d over mu times n plus a half minus h bar squared beta squared over 2 mu times n plus a half squared. Okay, so this is interesting. This side looks is sort of reminiscent of the harmonic oscillator states. Okay, with the n plus a half as the term that depends upon the quantum number n. But it has this additional term here. And you'll note that because reduced mass is always positive, and we got h bar squared beta squared, this is a positive coefficient here. And with the minus sign in front, it means that these are going to reduce the energy levels relative to the harmonic oscillator energy levels. Okay, as a preview, you can see that a little bit happening here. The harmonic oscillator energy levels are written in green here, and uniformly they are higher than the corresponding blue levels, actually starting here, the blue levels of the Morse oscillator. So indeed, the Morse oscillator's energy levels are decreased a bit relative to the harmonic oscillator energy levels. Now, to get an even better comparison for this particular set of oscillators, we noted before that to take a realistic potential, we could find the best fit of the harmonic oscillator to it by taking the second derivative with respect to x. Well, first of all, I'll note that if I take the first derivative of the potential here, this potential written up here, that I would find the following. I would get 2d times 1 minus e to the minus beta x times beta e to the minus beta x. And I'll invite you to go ahead and take the derivative of this function and see if you get that same thing. But you'll notice that as we go to x equals 0, which would be r equals r0, as x goes to 0, this term is going to be 1. 1 minus 1 is 0, so this must equal 0 at that point. Okay, what about the second derivative of the potential? Well, in this case, we get a little bit more complicated result, but still solvable. 2d times beta e to the minus beta x, quantity squared, plus 2d times 1 minus e to the minus beta x, times minus beta squared e to the minus beta x. Once again, this term will go to 0 as x goes to 0, but this term will not. This term will go to 2d beta squared. So in fact, this is what we can associate with our force constant from the harmonic oscillator, or more importantly, associate it with mu omega squared from the harmonic oscillator. So this means that our parameter beta, if we solve for that, would be equal to omega times the square root of mu over 2d. Okay, all I've done is take this equals this and solve for beta. All right, but what if we now plug this in to our expression up here for the energy levels? Okay, well now I'm going to get a slightly different expression. I mean, it'll have the same functional dependence upon the quantum numbers, but E sub n will be equal to, when I plug this in for beta, notice that the factors of square root of mu will cancel. The factor of 2d in the square root will cancel, and I'll get a factor of omega. So I'll have h bar omega n plus a half. So in fact, this term does become exactly the harmonic oscillator term for the harmonic oscillator that fits the bottom of the Morse potential well. And I think that hopefully this makes some sense, because if it didn't turn out that way, we'd have to scratch our heads and wonder why. All right, when we make the same substitution of beta into this constant up here, we end up with the following result. It's equal to h bar omega squared over 4d times n plus a half squared. All right, so this expression for the energy levels of the Morse oscillator actually is a little bit more useful simply because it gives us a connection to the harmonic oscillator with the first term, and the second term directly connects the harmonic oscillator h bar omega with the dissociation energy of the Morse oscillator. Now, we've noted before that whenever we have an anharmonic oscillator like a Morse potential, whenever we get to the point where the energy levels get so close together that they are no longer, the difference is no longer positive, that's the point at which we have exhausted all the bound states. So when we get to the point where, for example, the n plus 1th energy level minus the nth energy level is less than 0, that is to say, we didn't go up any more in energy, we started going down in energy, this is the point where we have exhausted all the bound states. So this provides us with a mechanism for finding out how many bound states there are in a Morse oscillator. And in fact, there's a formula that you can work out for that, but I'm going to let you do that on your own.